Dave Liepmann.
Thank you. Hi, folks. Is my mic on? OK. I'm Dave Liepmann. Like he said, I'm a freelance Clojure developer in Berlin. And I'm going to talk to you about a fun machine learning problem that I worked on in Clojure. And the really cool thing about this problem is that it takes actual fundamental properties of the universe that were discovered by Claude Shannon, who you see here, or over here, and it applies them to an actual engineering problem, an actual like real-world thing that people are using to do engineering. So what engineering problem are we talking about? The problem is how many clusters are in a data set. It's very straightforward. So here we have the same data set on the left and the right. On the left, it's split into 2 clusters. And on the right, it's split into 3, denoted by color. Now, which of these is more correct? Which of these represents or tells the story of the underlying data better? And how do we make that judgment? How do we make that judgment rigorously? That's the question I'm going to be working through. So to approach this problem, we're going to take some test data. And we're going to work through an algorithm called k-means. So we need some test data. How about we try to help solve the fight against cancer? That would be nice, right? So what we have is the Wisconsin Breast Cancer Database, which is about 650 samples of patient biopsies. And each one, you see the raw data on the left in a vector of vectors. Each one has 10 attributes in addition to patient ID, and you can see those on the right. And there are things like single epithelial cell size, it's a tongue twister, and number of mitoses that it's gone through. And notice the last attribute. We know the outcome, whether it turned out to be benign or malignant. That should make you sit up and take notice, right? So if we know the outcome, and we know all these descriptive factors of the breast mass, then hopefully we have a suspicion that we can do some sort of cluster analysis on this, and hopefully we find that there are 2 clusters, right? And hopefully those 2 clusters match the benign and malignant outcome, right? So what you would do is you would blind yourself to the patient ID, blind yourself to the outcome, and then run the cluster analysis. Hopefully you get this clean division between those without looking at it. So that's our hope. We've got our data. Let's get started. What's the first step when we're working with a new data set? You plot it, right? So we've got 10-dimensional or 9-dimensional data here, and we're going to cram it into 2 dimensions just to get some sort of a handle on it, because our brains are extremely well evolved to analyze and intuitively analyze visual data. So we took these 9 attributes, and you cram them into 2 dimensions using something called PCA, the principal component analysis, which is just some vector math. Don't have to worry about it right now. If you know it, that's great. But we've got some representation of those 9 attributes here. And I've actually included the outcome, the benign malignant classification, as color. And you can see right away, there's at least the suggestion that there's some clustering going on. We have some suspicion, right? You've got a big clump of malignant samples over on one side, and then this field of benign samples. So we have a suspicion. We have reason to believe that clustering will work. All right. So that's our data. Now I want everybody in this room to get pumped up because we are going to do some cluster analysis. Get excited. This is the fun part, OK? So what we're going to do is some k-means. And for the purposes of today's talk, k-means is just a black box machine learning algorithm. We're not going to worry about the internals. We're going to concern ourselves with the analysis of the k-means results, the analysis of the machine learning results. So we've got our familiar Clojure here. This black box function takes 2 parameters. The first being the data set, which is going to be the Wisconsin Breast Cancer Database, at least for most of the talk, and a number of clusters, which we're going to call k. I don't know why. And this k-means function says, if we assume that there are 3 clusters, this is where the clusters would be, right? And it says 3 clusters. Here are the cluster centers. They call them centroids because they have weird terminology. And there's the coordinate of the center of the cluster. That also tells you membership, so which samples belong to which cluster. And then it tells you the squared error. The squared error is a basic arithmetic representation of that clustering, and let's look at that in more detail. So what we have here is, to understand the squared error a little bit better, in case you're not familiar, is assuming we have 3 clusters. I've marked the center of each cluster in black, and then what we need to do to get the squared error, which is essentially just the distance from each point, is calculate the distance from that center to each individual sample, square that number, and then add it up for each cluster. And then for each cluster in the data set, each 3 of these, you add all of that up, and that's your sum of squared errors. That's a basic metric of how tightly packed your clusters are. And that's a basic metric of cluster quality, how well you clustered the data, right? Because what is a cluster? It should be density, right? A very spread out cluster with a large squared error, that's not really a good representation of a cluster. So why do we need this representation of the quality of our clustering? Because we told it how many clusters there are, right? We said there are 3 clusters. So you can't just tell it 3 clusters and then say, okay, great, now there are 3 clusters. We have to evaluate k-means multiple times. You have to say, okay, what if there are 3 clusters? We run that, and it says, well, if there are 3 clusters, here's where they would be, and here's the squared error you would get. Okay, run it again with 4. Here's where 4 clusters would be, if that was true, and here's the squared error. Same with 5, 6, however many clusters there possibly could be. So that gives you an evaluation criteria in the squared error. So let's plot that value. We have the number of clusters, which we're calling k, along the bottom at the x-axis, and then the amount of squared error on the y-axis. And you can see that with 1 cluster, you have a very high error, and then as you add more clusters, you get less, right? The graph is always going to slope like this. And that's going to be true in the general case, right? So more clusters means each cluster center is going to be closer to its samples. So that kind of throws a wrench into our evaluation criteria, right? We want to minimize error because density means good clusters, but we can't just increase the number of clusters willy-nilly, right? If you think about this slide again, what if we increase the number of clusters to the number of samples? We'd have a really great squared error because there'd be a black center over every single sample. The distance would be 0. That's not very helpful. So the common method, the most common wisdom for avoiding this predicament or fighting our way out is called the elbow method. Who's here heard of the elbow method? Okay, good. So the elbow method says you take this graph, which we know is always going to be sloped generally like this. It's going to continue downwards. And you look for the diminishing returns. You look for the point where there's some sort of inflection in the graph. And they call it the elbow. There's some sort of bend. And it's right there, right? That's it, okay? And that's it. We're done. We go home. It should feel kind of weird, right? That should make you a little uneasy. We didn't get into the internals of the k-means algorithm, but we did all this machine learning, complex math and all these computations, and there's all this rigor, and then we just kind of eyeball a graph. That doesn't feel right, or at least it shouldn't feel right. And don't get me wrong, there is a lot of value in just eyeballing graphs and getting a sense of things, but the elbow method is going to give you problems. It's not effective in all situations. So to take a step away from the data set that we worked on previously, if we look at some sample data that I just cobbled together, so we've got 3 groups, each consisting of 3 clusters. So there's clearly 9 clusters. I mean, like, hands down, there are 3 clusters. Oh, sorry, 9 clusters. Definitely 9 clusters, right? But I mean, there's something to say that there is 3 groups of them. The elbow method completely falls on its face, right? So it says there are 3 groups. That's all I know about. That's all I'm telling you. I'm not going to say anything about the underlying 9 clusters. You're on your own. And that's terrible, right? We want an evaluation criteria that tells us about the data. So this is clearly insufficient. So we need something more rigorous. And that's how I got hooked on this really awesome paper by Catherine Sugar and Gareth James. And it is awesome. I encourage you to read it. It's not, I mean, you're going to have to do that in your own time. It's called Finding the Number of Clusters in a Data Set, an Information Theoretic Approach. And this is where the jump method comes into play. So what they say is there's a lot of problems with using the elbow method to analyze the squared error. But all the information you need to make a judgment about how many clusters are in a data set is contained in that squared error. You just have to understand it better. So that deeper understanding is based on Claude Shannon's work. Claude Shannon, the CS pioneer, the founder of information theory, has an answer for us. So he pioneered information theory and with this statistical method of analyzing how you can send messages over a lossy channel and statistically, mathematically, rigorously understanding that. And one subfield, rather, of information theory is called rate distortion theory, and it's concerned with how much you can compress a given message. So rate distortion theory is one of those, gives us one of those tremendously fortuitous isomorphisms between two different fields. So what we have on one side is rate distortion theory, decades of math and research and proof. And the other side, we have a k-means problem. It seems completely unrelated. But we can model this problem as that problem, and everything goes away. So how do we model it? So think of your data as a message. All the 650 samples in our Wisconsin breast cancer database is a message that we're trying to send over a wire, one giant message of 650 points. And we want to compress that message as much as possible while maintaining as much of the shape of the original, or the shape or the feeling of the original data as possible. So we're trying to send that message, and we're trying to minimize distortion. So from the paper, I'll just quote, in exchange for compressing the information contained in the data, one must introduce some imprecision in or distortion of the original values. And they continue, the central problem in rate distortion theory is very applicable here. It's to find the best possible distortion achievable with a given amount of information. So right there, we've got it, right? We've got this way out of the failed elbow method predicament we were in. We want to balance the minimizing the error with the amount of information that we're sending. That was the limit, right? We don't want to just increase the number of clusters to the number of samples. And rate distortion theory has a rigorous method of doing this. We're going to go through this in Clojure. There is going to be code in the next few slides. Don't be worried. We'll go through it nice and slow. Our implementation is called the jump method, and we're going to go through it like this. The first step is we're just going to apply this information theoretic model, this model from rate distortion theory. We're just going to apply that to our data. And second, we're going to calculate what's called the transformed distortion. And then we're going to measure jumps in that transformed distortion as we increase the number of clusters. And then we're going to interpret those results. Okay? So I've got a subset of the relevant data here. So I only took a couple samples, and I got rid of unnecessary keys. We have the squared error and the number of clusters as a sequence of hash maps. And we have to apply the information theoretic model. All we do is reach into Clojure set and rename the keys. That's it. The squared error is now our raw distortion, just a mental change for us. So we've still got this graph, right, sloping down to 0. And now we have to calculate the transformed distortion. We have the results from the prior slide. So we've got a raw distortion according to the number of clusters. And that's still a vector of hash maps. And we're going to map over that vector of hash maps. And for each one, we're just going to create a new key. Right? You see the ASOC. And the new key is going to be transformed distortion. And the value for it is just going to be the raw distortion raised to the negative power of 2. You might say, why are we doing this? And that's a very good question. We transformed the distortion in order to invert the distortion curve, or the squared error curve. Because remember, it was always decreasing down to 0, and the values get difficult to work with at that level. So this is a trick actually from rate distortion theory that they use to just flip it upside down. So now it raises up into the sky, and it's easier to calculate differences between them. It's if this doesn't make intuitive sense, just trust me, it's a trick from rate distortion theory. That's all you need to know. So that was step 2. We applied the model, right, this information theoretic model. We transformed the distortion using this math trick from some other field. And now we have to calculate jumps in the transformed distortion. That's where the name of the technique comes from, the jump method. So it helps to use a metaphor here to see what we're doing. Suppose you're at the eye doctor, and they put you in this machine. And she says, which of these is more clear? 1 or 2? 2 or 3? 3 or 4, right? And you're looking at pairwise differences in the clarity. And the metaphor breaks down, but think of this as each clustering attempt, right? So each clustering attempt, remember, is an attempted compression of the data, of the full message, all 650 points. And we're doing the same thing. We're trying to say 1 cluster or 2 clusters, right? 2 clusters or 3 clusters, 4 clusters or 5 clusters, pairwise through the data. And this gives us a way to look at the squared error data in a better way. So again, remember the curve is always, of the squared errors, is always curving down. So we know that more clusters gives us less error. More clusters, less error, yeah. But what we want to say is how much less error, how much more clarity does that buy us? Think of it as spending another cluster. We don't want to spend another cluster if it doesn't buy us a lot more clarity. And so this eye doctor pairwise step helps us look directly at the improvement in message clarity from one clustering to the next. Okay? So in Clojure, we have, there's a lot of code here, but just at the top we have the results from the previous slide. In the middle we have the function, and at the bottom we have the results. Okay? So what we're doing is we are taking now, I have to put in a list form because it's going to conj. Conj the previous results with a transform distortion of 0. This is because we want to look at whether 1 is a good choice of clustering and 1 doesn't have a dance partner, so you have to give it a 0 to play with. And then we're just going to take that conged list or vector, whatever it is, conj produces a list, I suppose, and walk through it partition-wise. If you don't remember the arguments to partition, just accept that it does that pairwise comparison. 0 and 1, 1 and 2, 2 and 3, 3 and 4. And then for each one, we map over it, destructure the two of them, right, the pair, and associate a new value with the greater value, with the greater hash map. And that jump value is just a simple subtraction of the transform distortion, just a difference between the two. It's dirt simple. And the results you can see at the bottom, the relevant result is all the way to the right. And you can already see the jump value for k equals 2 is one of the largest, right? It is the largest. And that turns out to be the thing that we're looking for. We're looking for a large jump value. Big jump value means there's a huge improvement in message clarity. That means that it's a good answer for how many clusters there are. So this is the jump graph for the Wisconsin breast cancer data set, and it's pretty clear that if we're looking for a large jump value, that there are 2 clusters. That is a huge value for the jump at k equals 2. It's night and day, right? And this is actually a huge win for, it's a huge win for cluster analysis, for k-means, for the jump method in general, because it worked, right? And you look at the data, this is clustered results in color. So this is still blind to the actual outcome, and the results are nearly perfect. Proper k-means runs produces 2 clusters, and those 2 clusters are almost completely perfect to the actual outcome of benign or malignant samples. So that's a huge win. It's really fantastic. And let's look at the comparison between the elbow method, which, okay, I guess there's an elbow here at k equals 2. Sure. Maybe there's one somewhere else. You could convince me at like 4 or something. I don't know. But the jump method is absolutely clear. It tells you what is in the data very, very straightforwardly. There is no guesswork. There's no eyeballing the graph and saying maybe. And if it is unclear, you can just use apply max, and it's a valid answer. The largest jump value is the answer. So how much time do we have? Are we doing okay? Okay, great. So we'll do a small detour. So you might say, well, I can see that that k equals 2 in this case with the jump method, but I can also see k equals 2 in using the elbow method. And the authors of the paper, the Sugar and James paper, go into this. They show half a dozen data sets where the elbow method just falls flat on its face, like the earlier example I showed you. So here, for instance, you have 4 Gaussian points, just some random sampling around 4 well-distinguished, well-separated points. And the elbow method does fine, right? No problem. But as soon as you start intermingling the data, as soon as there's some more noise, it starts to become more difficult. Is it 4? Is it 7? What's going on? The data is not telling me what it knows. And you can prove that it knows this because this is the squared error. But the jump method, so the elbow method says, I don't know, but whatever. The jump method is absolutely clear. There are 4 clusters. It sees what's in the data much, much better. So I have one final point before I start to wrap up and talk about methodology. The paper I implemented had a lot of sections like this. And I can read mathematical notation. I can push through and get all of this. But it can be intimidating, right? Especially if you don't have a formal math education. This is pretty dense. So once I read the paper, once I really knuckled down and pushed through and understood not just the math, but the concepts underneath the math, the concepts underlying what the authors are trying to tell you, the code is pretty straightforward, right? That's Clojure, right? So this is kind of stacking the deck because there was a couple hundred more lines of code with bootstrapping the data and with a pull request to a library so it covered my use case and visualizing the data. There's a ton of more code that is actually in there. But the relevant code from the paper, I mean, that's all the code that we do, right? We're programmers, we do that. The relevant code from the paper is this, really. That's the center of the code. And you might say, well, I don't understand that code. Maybe we've got some new people in here. That's fine. If I went through this too fast, if maybe you don't memorize the way that vector destructuring works inside an FN parameter list, maybe you're not familiar with anonymous functions or something, that's all fine. Because I know that everyone can get this. Everyone who can fire up a REPL can get this because a REPL lets you run it. A REPL lets you see what's going in and see what's coming out and play with it in the way that mathematical notation in a paper doesn't. Right? So this is a much more powerful way to explore complex concepts in the scientific literature than publishing a step-by-step word algorithm and no data, no sample data. And this is all on GitHub. This is in a set of a couple gists that's in a kind of literate coding format, so you can follow through as we build each of these functions. That's what I have to say about that. Is that you can do this too. If you have an interesting paper that are floating around maybe the Clojure community, a lot of the luminaries are tweeting papers from computing history that are relevant. Read it again. You're not going to get it the first time. Read it a third time. Read it a fourth time, and start implementing it in your REPL. So you can implement your favorite papers too. So let's talk about tooling. A quick review of what I used to get here. And this is something where I think a lot of you guys could actually give this part of the talk, right? So I used Clojure. What are the things we like about Clojure? Well, it was we're working in a functional programming paradigm, and so it was super easy to pipeline the data. That was super great. It was super easy to prototype the data because I used Emacs and Cider, and I had an in-buffer REPL, not a line-by-line REPL, but one where you have a persistent file, and you can walk up and down and evaluate inner parts of the function and outer parts of the function and give it different data and have a prototype here and then write a whole new prototype next to it and have them next to each other. And I find that super useful. I used Incanter for my data visualization stuff. That was a lot of fun. It was very straightforward, except for converting between different data formats. And the k-means algorithm, or k-means library that I used is Weka, which is wrapped by clj-ml. It was a fine library. It was nice to use. In the future, I would probably just write k-means myself, because talking to a Java black box is not always the most fun, especially when it's behind a wall of macros. that ended up being one of the pull requests and a lot of trouble to debug stuff. Anyway, so that's what I have to say. It was a lot of fun. Thank you, Clojure Berlin. Thank you for having me.
Thank you. Questions from the audience?
Sorry, it's me again. I'm actually having 3 questions belong together.
Okay.
One is I doubt your ground base is you're deleting the outcome of the cancer test to find 2 clusters.
Mm-hmm. Yeah.
That's I think it's just a mix-up because
so you
don't find 2 clusters matching exactly the outcome. Usually you find clusters to run your tests, your medical tests in.
Yes.
And you have to group by that. So that's one thing.
Yeah, keep a separate test set. Sure.
Yeah, that's just for
for
the sake of completeness. The next thing is k-means is an algorithm which might run into local minima.
Yeah.
So if you implement the dump mechanism on it, this is you're totally right. The idea is great, but your basic problem is if you run into a local minimum, the number of clusters might be just wrong for that, or the error for that number of clusters is just wrong, and you might have artificial jumps in your data.
Yeah, yeah. So the authors of the paper address that in a couple different ways. First, you really shouldn't be running just one k-means. You should be running a whole bootstrap data set, get error bars. I didn't have time to get into that. That is in the gist that's on GitHub in more detail. There was another point to that, which is that the local minima. Yeah, so specifically how they address, if k-means is finding local minima that are wrong, that's what the data is. It's not, this is an analytic method on top of k-means. It can't fix k-means. It's just, it deals with the good and the bad of k-means. Yeah. But the point of this is that if k-means has something to say, it will tell you, whereas other methods leave you in the dark.
Yeah, exactly. And why I was coming to that point is, like, I'm totally on your side to try stuff out, prototype, even on research papers, but don't forget the other side. Think critically about what you're doing. Sure. Which is what a lot of people trying out stuff in the REPL is just missing, and I wanted to point that out. Thanks.
I just wanted to know, did you file a pull request for David Liepmann to get it into Incanter.org?
No, it was not in Incanter. It was in clojure-ml because the underlying Weka library supports different initialization methods. So I didn't talk about that, but k-means is very dependent on initial cluster placement. And Weka supports various methods. Clojure-ml did not, and there was a good deal of wrestling with that to even realize what was going on. So I just added support for it. Yeah, that was actually another failure point was clojure-ml uses keyword arguments, and so it was accepting my keyword arguments for a keyword argument that it didn't care about, and it was just tossing it away. Made me very sad. Okay, any other questions?
So, thank you again.
Thank you.
There's a coffee break right now, and we continue.